Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. Let's see this problem. We are given a number n and our task is to find total number of set bits from 0 to n. So to understand this problem better, let's see few examples. Let's say if n equal to 5 and these are the binary representation of numbers from 0 to 5. And you can see there are 7 set bits from 0 to 5. 1, 2, 3, 4, 5, 6, 7. So the output is 7. If we consider n is equal to 4, then these are the binary representation of number from 0 to 4. And you can clearly see that there are 5 set bits from 0 to 4. 1, 2, 3, 4, 5. That's why the output is 5. We have already solved this problem in previous video. And in previous video, we have used recursion to solve this problem. And this video is a continuation of the previous video. In this video, we are going to solve this problem by using more efficient approach. So if you have not watched the previous video, then I highly recommend to watch that video, come back here and continue watching this video. Okay, in previous approach, we saw the efficient approach to solve this problem. And that approach took big of log n time to solve that problem, and it also took big of log n space, right? And it was a recursive solution. But in this video, we are going to see more efficient approach, and this approach is going to take big of log n time and only constant space because it is a iterative solution. Okay, so let's see how we do it. So before we move on to implementation of this efficient approach, let's discuss the idea for efficient approach. Let's consider the value of n is 12. Okay, and here I have written the binary representation of numbers from 0 to 12, and this is the first position, this is the second position, this is third, and this is fourth, right? So what we do in this approach, we consider each position at a time. It means we only consider first position at a time, then second, then third, and then fourth. And then after considering one position at a time, we are going to divide these bits into group of zeros and ones. Okay, as you can see that in first position, you can see there are few groups of zeros and ones. 1, 2, 3, 4, 5, 6. And if you consider second position, you see there are groups of 4 elements. And in each group, you can see that there are 4 elements. And in first position, you can see there are 2 elements. Okay. So if you observe this binary representation, you can realize that in each group, each position has elements in power of 2, right? So if you consider first position, there are 2 elements in a group. If you consider second position, there are 4 elements in group. If you consider third position, there are 8 elements in this group. So all elements in each group is a power of 2. Okay. So in first position, there are 2 elements, then 4, then 8, and then 16. Okay. So we have groups with 2 elements, 4 elements, 8 elements, and 16 elements. So these are the observations we have made so far. So now our task is going to be simple. Now we just have to count number of groups at each position, and then we have to count number of set bits in each group, right? So if you consider position 1, you see that there are 6 groups of zeros and ones. Okay. And in each group, there is only 1 0 and 1 1, right? So how many set bits are possible? Obviously 6 groups into 1, 6 bits are possible, right? So this way we are going to consider each position and count set bits in each position. So let's see how we do it. So first of all, we have to count how many bits are there in all the position. Okay. So it comes out to be 13. Why? Let me show you. Do not get confused with 12 and 13. I am talking about number of bits. Okay. So if we count number of bits from 0 to 12, it comes out to be 13. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So we are considering number of bits, and then we are considering each position. So in each position, number of bits are going to be 13 only, because all positions the number of bits remain same. Okay. So now let's consider the first position, and in this position there are groups having 2 elements. Okay. So let's see how we find the number of set bits. Okay, so this step number 1 is taking first position in consideration. Here the group is having 2 elements. Okay, so far so clear. So how many groups are possible? If we have 13 bits and if we divide 13 by 2, it means we are finding groups having 2 elements. So it's going to be 13 divided by 2 is equal to 6. It means there are 6 groups are there. Now, how many set bits in each group? It is going to be equal to total elements upon distinct elements. So how many distinct elements are there? In case of binary, there are only 2 distinct elements are there, 0 and 1. So if we divide 2 by 2, we get 1. It means in each group, the set bits is only 1. So now we can easily calculate how many set bits in there in first position. It's simply equal to 6 into 1. It comes out to be 6. So our first position is done. So at first position of the binary representation of number from 0 to 12, there are only 6 set bits. So far so clear. Now let's move on to second position. In this position, we have to find groups of 4 elements. So how many groups of 4 elements are possible? It's simply 13 divided by 4, that is equal to 3. Okay, and you can see that there are 3 groups are possible in second position, 1, 2 and 3. Now second thing, how many set bits in each group? Each group has 4 elements. So how many set bits are there? It's simply 4 divided by 2, because 4 is the total elements and 2 is the distinct element. So 4 divided by 2 comes out to be 2. So this way, now we can calculate how many total set bits in second position. So it's simple. Number of groups into number of bits. 3 into 2 is equal to 6. So we are done with second position also. Now only 2 positions are remaining. So let's see third position now. So in third position, we are going to count number of groups of 8 elements. So we simply divide 13 by 8, we get 1. It means only 1 group is possible. And how many set bits in each group? It's simply total elements divided by distinct elements. Total elements are 8 divided by 2 is equal to 4. So the set bits in third position is going to be 1 into 4, right? Because 1 group is possible and in each group 4 elements are there. 4 into 1 is equal to 4. Now here if you observe, after finding the group, few elements are remaining, right? Because this is not a complete group. In this group there are 8 elements, but in this group there are only 1, 2, 3, 4, 5 elements are there. And there is 1 set bit in this group. So we have to count this also. So let's see how we can calculate this. So first of all, we have to calculate how many remaining bits are there. So how we calculate remaining bits? So when we do modulo of 13 by 8, we get remaining bits. Okay, how it is giving remaining bits? Because when we divide 13 by 8, we are calculating how many groups are possible of 8 elements. Okay, so when we divide 13 by 8, we get some remainder, and that remainder is nothing but a remaining bits, right? So it means 13 is divisible by 8 one times and 5 is the remainder. So it means 5 bits are still there. Okay. Now how many unset bits are there? So unset bits are obviously equal to set bits, because if a group consists of 4 elements or 8 elements, so there are 4 zeros and 4 ones. So unset bits are also equal to 8 divided by 2, that is 4. Now here is a trick. Now we can calculate how many set bits are there. Okay, how? See, remaining bits are 5 and unset bits are 4. Means there are 5 bits remaining, and out of 5 bits, only 4 bits are zeros. It means there is 1 bit that is set. So how we can calculate this? Simply subtract 4 from 5. We get the set bit, and that is 1. And we can verify this, that in third position 1 bit is set, and we have counted this bit also. Okay, so we are done. So the total set bits in third position comes out to be 4 plus 1, that is equal to 5. So third position is also done. Now let's move on to fourth position. In fourth position, we are going to count number of groups having 16 elements. Now here, how many groups are possible? 13 divided by 16, 0. Why 0? Because in fourth group, if you observe this carefully, there are less than 16 elements. Okay, that's why we are getting 0, because we are not able to find any groups of 16 elements. Okay, No worries, let's continue. So how many set bits in each group? 16 divided by 2, that is equal to 8, but we do not have any group. So that's why number of set bits in 4th position comes out to be 0 into 8, that is equal to 0. But we are not yet done, okay? So let's count the remaining bits. So when we do 13 modulo 16, we get 13. It means 13 bits are remaining. And how many unset bits are there? 16 divided by 2, that is 8. It means there are total 13 bits. Out of 13 bits, 8 bits are unset. So we can easily calculate the set bits. Simply subtract 8 from 13, we get our set bits. So there are 5 set bits at this position. Okay. So the count of total set bits in 4th position comes out to be 0 plus 5. Okay. So 4th position is also done. Now let's move on to 5th position. Now why we are doing 5th position? Because I am only considering the 4 bits. But if you use Java, then there are 32 bits representation of integers. So it might be possible that you get more ones after 4th position, right? Okay, now let's consider 5th position. Here we are going to find group of 32 elements. But when we divide 32 by 2, we get 16, and that is greater than 12. So here we have to stop. And the reason is simple. We have considered 4 bits, and in 4 bits there are 16 numbers are possible, because 2 to the power 4 is equal to 16, and our n is only 12. So we do not need to go beyond 16, because if you go beyond 16 you only get zeros. If you consider 32-bit integers, then after 16 you get all zeros, right? So no need to check after 16. So this is our stopping condition. So far so clear. So here it is an implementation of this efficient approach, and in this approach we are not using any recursion. It's a simple loop implementation. So let's see how it works. So here we have a function count total set bits iterative, and this function is taking n as input, and the first step in this function we are doing is n equal to n plus 1. Why? Because if n is equal to 12, the number of bits at each position from 0 to 12 is going to be 13. That's why I am adding 1 to it. Then we are initializing a variable count of set bits that is equal to 0. Okay. And the next variable is distinct elements. And how many distinct elements are there? 2, 0 or 1. And then we begin our loop with 2, because minimum elements in any group is equal to 2. So we begin this loop with 2. And in each iteration we are checking if elements divided by 2 is less than or equal to n. And this is exactly we have discussed here, that if elements is greater than n, then simply stop. Okay. And then we are simply doing elements into 2. Means every time we are incrementing power of 2 by 2. Okay. So let's understand this with this input. Let's say if n is equal to 12, then we update the value of n to 13. The initial value of count is 0. D here means distinct elements, that is equal to 2. Okay. So when we run this loop, in first iteration our E is equal to 2. So how many groups of 2 elements are possible? N divided by elements. N is what? 13. 13 divided by 2 is 6. Okay. And count of set bits comes out to be elements divided by distinct elements. 2 divided by 2 is 1. Okay. So count is going to be, our count of set bits going to be 6 into 2 divided by 2, that is equal to 6. Okay. Then we simply calculate remaining elements. Here it comes out to be 1, and unset bits is also comes out to be 1. So we are not going to get into this if statement. Okay. So in next iteration our E becomes 4, because we are multiplying 2 with element. So now we are going to search group of 4 elements. So how many groups are possible? 13 divided by 4, that is equal to 3. And our count is going to be previous count plus 3 into 4 divided by 2, that is equal to 12. Okay. Let's say, count remaining elements. So if we do 13 modulus 4, we get 1. Okay. And unset bits are 2. So here also remaining is less than unset bits, so we cannot do anything. Okay. Let's move on to next iteration. In next iteration our E become 8. Okay. So how many groups are possible of 8 elements? 13 divided by 8, that is equal to 1. So count is equal to previous count plus 1 into 8 divided by 2, that is equal to 16. So far the value of count is 16. Now let's count the remaining elements. Remaining elements are going to be 13 modulo 8, that is 5. And unset bits are 8 divided by 2, that is equal to 4. This time remaining is greater than unset bit. So we count how many set bits are there. So set bits are going to be 5 minus 4, that is 1. So count is going to be previous count 16 plus 1, that is equal to 7. Okay. So third position is done so far. So let's move on to fourth position. So at fourth iteration, our E becomes 16, and how many groups are possible? 0. And the count of variable remains same as 17. Now this time the remaining elements are going to be 13, unset bits are going to be 8. So we are going to count number of set bits, that is equal to 13 minus 8. So the previous value of count plus 13 minus 8 is going to be 22. Okay, so moving to next iteration. In next iteration, our E becomes 32. And this is where we stop, because 32 divided by 2 is 16 and 16 is greater than 12. So at this point, our loop gets terminated and count of set bits gets returned to our parent call. And the output of this input is going to be 22. So it means there are 22 set bits between 0 to 12. Okay, great. So far so clear. Everything is working fine. So now let's talk about the time complexity of this function. So to calculate time complexity of this function, we have to figure out how many times this loop is running. So it is clear that the loop is running log n times. Why? Because we are multiplying elements in each iteration by 2. So whenever we divide or multiply anything by 2, we always get time complexity as log of n. So the time complexity of this function is big O of log of n. And talking about the space complexity, we are not using any extra space to solve this problem. We are simply using some variables and constant space. That's why the space complexity of this solution is theta of 1. And if you compare the space complexity with the previous approach, which we have discussed in previous video, you see that there is a significant difference in space complexity. In previous approach, we were using log n space, but in this approach, we are only using constant space. Great. So let's have a quick recap of what we have done so far. So we are given a problem to find total number of set bits from 0 to n. And we saw the efficient approach to solve this problem. And in that approach, we simply considered the first position of the binary representation from 0 to n and count the total number of set bits. Then we considered next position, then next position, and then next position. So this is how we calculate all the set bits from 0 to n. And in this approach, time complexity came out to be big O of log of n, and space complexity came out to be theta of 1. So I hope you like this solution. So this is it for this video. Thanks for watching. See you in the next video.